edge, near the joint, and then near the corner. At night, this is the most critical condition. Okay, so we want to know the maximum stress at night. This type of analysis should be done with considering the effect of temperature differential. Okay, this shows this is the difference between the temperature at the top and at the bottom. Okay. We also look at the simplification. Typically, the temperature plot is a nonlinear plot. To simplify the computational procedure, it's simplified by a linear approximation. Okay, what happened if we assume it to be linear and we calculate the stress, and we found out that, well, when the temperature distribution is assumed to be linear, the maximum computed stress tend to be higher for the daytime condition and lower for the nighttime condition. Okay, what does it mean? It means that if we assume it to be linear, we calculate the stress. The calculated stress is actually higher than what it would be, okay, for the daytime. But at night, it's actually lower. Okay, but however, for Florida condition, the daytime condition is more serious. So if we want to look at the most serious condition, and we assume it to be linearly, the temperatures to be linear distributed, we get a more conservative estimate. So this is the conclusion. Since the maximum stress in the daytime is usually higher than that at night, using a linear temperature distribution results in a higher estimation for the maximum stress. So for design purpose, we will end up with a conservative estimation of the maximum stress if we assume it to be linear. Okay, now the picture is now different. Okay, what we had known before may not be true anymore. Okay, now we analyzed the effects of the various factors by assuming a temperature differential. Okay, here is a plot of maximum stress versus margins of subgrade reaction. Okay, and these plots are for the condition when there is no temperature differential. Okay, when there's no temperature differential, subgrades, the margin of subgrade reaction has a significant effect. Okay, and what we had known before is that when you build concrete on a stiffer subbase, if the subbase is stiffer, you can use a thinner concrete layer, right? But that is if it's fully supported. Okay? If it's not fully supported, if there's a temperature gradient, that may not be true. As you can see in this thing here, the stress could actually go up slightly. It depends on the length and so forth, but the stress could actually go up as the subgrade stiffness increases. Okay. And not only that, the stress is much higher than if it's not, if there's no temperature differential, and the stress could be as high as 2 times as much. Okay, and this is this match with our observed performance. The concrete was found to with a concrete pavement with a stiff subbase was found to have cracked, and with concrete pavement with a stiff subbase could crack even more. Okay. This is contrary to what we have known conventionally, because conventionally we analyze it by assuming that the concrete slab is fully supported. When it's not, then we having a stiff subbase may not help. Okay, and so this is the conclusion. When the effect of thermal gradients are considered, the effect of subgrade stiffness has very little effect on the maximum stresses in the concrete slab. The use of a stiff subgrade or subbase may not necessarily improve the performance of a concrete pavement. Okay. And also the slab length now has a great effect, while before it has no effect. So here it's slab length, maximum stress versus slab length. When there's zero temperature differential, it's basically flat. Okay, slab length has no effect, but when we have a temperature differential, the higher the slab length, the higher the stress would be. And also, the temperature differential also has a great effect. So we need to know what the temperature differential for the region might be. Okay, so here's another conclusion. When thermal gradients exist in the concrete slab, the maximum stresses increase with increasing slab length. Now slab length becomes a design, a parameter that we need to consider in the design. Okay, and that is supported by our observation. We look at this pavement that's I-10, which had a variable slab length. We did a condition survey for the slabs that are shorter, 4.9 meter and 5.2 meter, versus the slabs which were longer. And the slabs which were longer had a significantly higher percentage of cracked slab. Okay, and other properties also now have an effect, such as the coefficient of thermal expansion. Before, it's not part of the equation. Now, we use a concrete with a higher coefficient of thermal expansion. The resulting stress is going to be higher. Okay. And the elastic modulus, of course, have an effect. Well, elastic modulus have similar effect also in the conventional way of calculating stress. But you know, when the temperature effect is considered, it has an even greater effect. Okay, so I said that this is the analysis, the result of the analysis, and we want to come to see if it matched with observation. We went out and look at pavements that cracked versus not cracked, or for the ones that are cracked, we measured the percentage of cracked slabs, and we took cores and measured the elastic modulus, and this is a plot of percent crack slab versus elastic modulus of concrete. And interestingly, the pavement with a concrete with a higher elastic modulus actually crack more. Okay. This is kind of surprising because concrete with a higher elastic modulus are stronger, right? Okay, and so why would the stronger concrete crack more? Well, the stronger concrete had higher elastic modulus, and when you have higher elastic modulus, the resulting stress is higher. Okay, so if the strength does not increase proportional to the increase in stress, it may crack more. Okay, and in this case, it actually cracked more. The stronger concrete has actually a worse performance. Okay, usually show that the elastic modulus is related to the strength. In this case, we didn't have the flexural strength, so we plot against the compressive strength. So, it shows that the stronger concrete actually crack more. In this particular case, I'm not saying that it will crack more. It depends on the situation. So we have to do an analysis. So if you're comparing different concrete mixture to see which one would perform better, we cannot just judge it based on strength alone. A concrete with a stronger strength, with a higher strength, may not perform better. We have to do proper analysis. Okay? So here's my general statement. Maximum temperature low induced stress, which means that it's the maximum stress under the critical condition, increase as the concrete modulus and coefficient of thermal expansion increase. So if you have a concrete with a high elastic modulus and with a high coefficient of thermal expansion, your expected stress is going to be higher. Okay? And having a stronger concrete may not help because your stress may be too high that even though you have a higher strength, it may not compensate for the increased stress. A concrete giving a lower maximum stress to flexural strength ratio would give a better performance. So if you want to evaluate between different concrete mixtures, we need to do the proper analysis. The one that give us this lower stress to strength ratio would theoretically give us a better performance. Not just strength, or not just, you cannot judge it just based on one parameter. Okay, you know, we cannot say that, well, this concrete, because it had a higher coefficient of thermal expansion, it may be worse. Well, it could be worse, but we have to look at the whole picture, okay, and judge it based on stress to strength ratio. Okay, and so other effects similar. You need to have good load transfer at the edge. So when we have thermal gradient versus no thermal gradient, they're similar, but it also shows that we need to have good load transfer at the edge and at the joints. You know. Another thing that will greatly help to reduce stress is if we have bonding. If we have two layers of material, if they are bonded, it helps a lot. Okay. In Florida, there was an experimental roll where a thin layer of concrete is placed over an econocrete layer, and most of them were bonded, but on a few test sections, they were not bonded. And for the unbonded section, it failed pretty much right away. Okay. And when we did the analysis, it showed that if they're not bonded, with the effect of temperature differential, the stress, the computed stress was much higher than the flexural stress. In this case, it's 186% of the stress of the flexural strength of the concrete, and no wonder it failed right away. But for the rest of that test section, they were bonded. In fact, this experimental roll was built about 40 years ago, and it's still in fairly good condition today. And the reason was because this concrete was bonded to the econocrete, and now it acts as one thick slab. Okay. And now, because they're bonded, the stress becomes much lower, and you have to analyze it by considering the temperature effect. Otherwise, we do not get the true picture. Okay, and this is the analysis of the I-75, the one with the long slab that broke in half. This was constructed with, it was concrete over the econocrete, but it was not, these two layers were not bonded. And so we have relatively higher stress. If they were bonded, the stress would be much lower, and the percentage of this stress to strength ratio would be lower. But this was not done. Okay, well, of all the factors affecting performance of concrete, what is the most important factor? Well, the most important factor is the slab thickness. Okay. As you can see, this is maximum stress versus slab thickness when temperature differential is not considered, when there is a temperature differential of 20 degree F or 11 degree C, the stress is much higher, but also we can also see the great effect of the thickness of concrete. You can see that if we want a concrete pavement to last longer, if everything is done right, what can we do to increase the life of the concrete pavement? The easiest way is to increase the thickness. Okay, if you increase the thickness by 1 inch, 1 or 2 inch, 2 inch or 5 centimeter, that concrete pavement, the life of the concrete pavement could more than doubled. Okay. So what is the design of concrete pavements today? Okay, in Florida, this is the design used for concrete pavement today. Okay. Concrete pavement is not used very often in the United States. On the average, about 5% of the expressways of the paved roads use concrete. Okay. And it's true in Florida, about 5% of the roads are paved with concrete. And concrete is used when we want to design a road that would pretty much last forever, 40, 50, 60 years long. Okay. And as I mentioned in my last presentation, asphalt pavement usually would last only for, on the average, 12 years because of the problem with age hardening. But with concrete, if concrete is properly designed, it could last for 40, 50, and 60 years. Okay, and so this is the design used today in Florida. Okay, now the typical design thickness is 33 centimeter. Okay. On the edge, it has a widened slab that extends to the shoulder by 2 feet or 0.6 meter. Okay, because the stress is most critical when the wheel is close to the edge. But if you make the slab wider and you mark the lane properly, so it's less likely for the truck to go to the edge of the slab, because if you mark it as the edge of the lane, even if it goes to the edge of the lane, it's still 0.6 meter away from the edge of the slab. And now this emphasis on drainage, this edge drain. I'm going to show a picture of an edge drain. And the material used is a drainable material. Okay. This soil with maximum amount allowable material passing the 200 sieve. And in order to put the concrete paver on it, this subbase needs to be strong enough. So if all we have is this soil, it's impossible to put the concrete paver on top of it. So usually you would stabilize it with rock and compact it before the concrete paver could be put on top of it. Okay, this is not for reducing the concrete thickness, but this is put down so that the concrete could be properly placed. Okay, and this is a summary of the design used. Okay, jointed plain concrete pavement, typical thickness 33 centimeter. Typically, we have a widened slab that extends into the shoulder to reduce the stress. The subbase usually is made of a drainable material. Okay, and if it's made of a soil, it needs to be stabilized at the top so that it can withstand the heavy paving equipment. The transverse joints are dowel. Spacing is 4.6 meter. Okay. Other besides the A3 soil, we could also use an asphalt treated permeable base. So whatever water that got underneath the slab would drain off fairly easily. Okay, but underneath this asphalt treated permeable base usually there would be an asphalt subbase so that the water would not